Okay, hello and welcome. This is Stats 102B, Computation Optimization for Statistics, and we're doing this during the summer. I want to encourage you guys to sit closer to the front. It's, I don't know, like as far as like my vision goes, I mean, like I can see you in the back just fine, but like my brain is only really able to focus on like, I would say the first two rows. So, um, as far as like phases and stuff. But anyway, my name is Miles Chen, and I'll be your teacher this quarter, or I guess this summer session. And yeah, I'm looking forward to this class. I taught it during spring quarter. I think it went well. This is summer, so it's going to be fast. It's going to be fast. Have you guys taken classes in the summer before? Yeah. Okay. All right. So you just know it's like another level of intensity. Okay. All right. Highlights from the syllabus. Let me move this over here because what did I write? I wrote my name is Miles Chen. You can call me Miles, or you can call me Professor Chen or Dr. Chen, whatever you are comfortable with. That's fine. I think this is correct. If there's a difference, go with what's in the syllabus, not my notes here. Okay, but we got lecture viewing quizzes, Campus Wire. I'll send out invitations to Campus Wire. We have homework. There's a midterm exam and a final exam. So we've got 2 exams in the class here. Okay. I don't curve, straight scale, so that's there's different philosophies for grading, and I'm a straight scale kind of grader here. Okay, lecture view quizzes. Some of you have taken classes with me before, and if not, this is kind of how I do quote unquote attendance. I don't do attendance. I don't like call out your name and see if you're in the classroom. I know sometimes people miss for whatever, and I'm recording video of the lecture, and so if you aren't able to attend live in person or something, you just have to watch the video. And during the lecture, I will give you answers to the view quiz. So, for example, if you open today's is week 1 Monday lecture view quiz. For me, it says preview. Yours will say like begin quiz. Okay, and it's just multiple choice questions, no context. Okay, there's no way to get the answers without I guess watching the thing here. Okay. The first one, the answer is the letter E. E as in elephant is your first view quiz answer. Okay, E. And so jot that down, and then when the lecture is done, you can fill out all of your answers. Make sure you take the time to double check that you selected the correct answer choices. Okay, if you mistakenly click the wrong answer, that's too bad. Okay, and then treat this like a quiz. So if a classmate said, "Hey, what's the answer to the quiz?" you wouldn't, that's cheating, right? And same thing with this. These are low stakes quizzes, but still, please treat them like a quiz. You're not doing them any favors by giving them the answers. Okay, and I will give you the answers to questions 2, 3, and 4 later today. But for today, your first answer is the letter E. Okay, and then the important thing is that these quizzes close by the time the next lecture begins. So our next lecture is Wednesday at noon, and so make sure you respond to the quiz before Wednesday noon, okay? Because it closes, and that's it. Game over. So we have that, okay? All right, questions about the quiz, how that works? Hopefully that makes sense. So that's that. First answer today is the letter E. E as an elephant. Okay. And again, if you miss class, just watch the video that's recorded. I usually try to get them posted on YouTube and things like that. Okay. Homework. You'll upload your homework you'll knit your homework as a PDF, and then you'll upload your PDFs to Gradescope. So I post homework. There'll be RMD files. You'll download them. You'll answer the questions. You'll knit them into PDFs, and then you'll upload your PDFs to Gradescope. If you need an extension, contact me, okay? Or if you have documentation, you don't have to contact me. You can just attach your documentation to the homework. Oh, one other thing. Okay, so so it's summer, 6 weeks, 2 classes a week, okay? And so 2 of those classes are also exams. So we have week 6, Wednesday is the final exam, and then week 3, Wednesday is going to be your midterm exam, okay? So we really only have 10 lectures, but then we have, there's Labor Day, okay? Which is a great holiday, but like that eats up a thing. So I'm sorry, but I can't afford to lose like an entire, like 1/10 of the class. So we're gonna have like a makeup lecture, and I'll record this video and I'll post it up on Friday, okay? And I mean, I don't know how you as students feel about having this extra class and things, but you know, I want to make sure you get your money's worth too. But yeah, I'm sorry. The Labor Day, you know, we won't meet. We won't be on campus, but I will have an online lecture the Friday before. Okay, sorry about that, but that's what we'll have there. Okay, so to kind of make up the missed Labor Day, and that's what we've got there. Okay, all right. So let's talk about what is this class about. Has anyone taken 101C? Okay, one person. Okay, or maybe 2 people. Okay, so 101C is, I don't know, statistical learning. You fit models and stuff to your data. And this class, there is, I would say it's a class on foundations for data science. There's a lot of overlap, but I approach this class a little bit differently than 101C in that I put a lot of emphasis and focus on kind of the computation and the mechanics of these machine learning algorithms. Whereas, you know, 101C, I would say is more about the application to data sets here, okay? So here, we're not gonna be working with like real data sets very often, mostly kind of toy data sets or specific data sets versus 101C, you know, maybe you're working with like real data a little bit more, okay? There's like, I don't know, you know, when you explain to people and they say, hey, what are you studying? And you say, oh, my major is statistics and data science or data theory. You know, depending on who you're talking to, people might wonder like, oh, what is that? And I don't know, do you guys have an answer for what data science is? Because you should have an answer, right? Because this is a common question, right? Anytime you meet with family at some point, they say, oh, how's school going? Oh, what are you studying? And then they might go, oh, that's neat, or oh, you're so smart, or the other one, what is that, right? What is data science, okay? And so you should have an answer for data science. So yeah, what were you gonna say your answer is for what is data science?
Oh, I was just like telling a story behind numbers.
Telling stories behind numbers, okay. All right, I like that. Anybody else for answers? Yeah.
The relationship between the variables and find out a model.
Okay, I mean that's a good answer, but I'm thinking like we're talking to grandma here, right? and what kind of answer can you give to someone's grandparents? Like, right, what is data science? And I don't know. I think one answer is kind of, you know, data science. I would say is kind of a blend between computer science, coding, along with statistics, you know, analyzing data, right? And we're trying to extract meaning, and you can say, oh, you know, and that's what powers all of the, you know, the algorithms that decide what video you're going to watch on YouTube next, or what shows up in your Facebook feed or on TikTok or whatever, right? Those are all kind of applications of data science algorithms, and it's really a combination I would say, of kind of the coding that is part of computer science, and then kind of this math and stats knowledge. And so Drew Conway said, here's a Venn diagram. And it says data science is kind of coding skills, math and stats knowledge, and then domain expertise. Domain expertise basically means you can't just blindly apply coding and math and stats knowledge if you don't know the subject that you're studying, right? Like if you're gonna be doing data on, say, on sports, on like baseball, okay? And if you've never watched a game of baseball, or you don't know anything about baseball, you will be significantly hindered in your analysis of this data, okay? Similarly, if you say, all right, I'm gonna do some, I don't know, breast cancer patient data, okay? And if you haven't done any, if you don't know anything about medicine or cancer or breast cancer or things like that, you will be significantly hindered. And so it's important that you team up with somebody who's very knowledgeable, or you yourself learn about that subject in order to kind of to learn about that, right? And so that's kind of what this this diagram is. Hacking skills, he writes hacking skills, but it's kind of this being able to work with a computer, because at this point all of our data sets are so big that you cannot handle them by hand, right? Early statistics, have you guys taken Stats 101B? Okay, in Stats 101B, that's like ANOVA design of experiments. That comes from a time where your data sets were small. It was really expensive to gather data. There's kind of this picture, so like in 101B you learned about like a Latin square for your design of factors and things like that, and they would apply it for like agriculture, and you would have to grow some wheat under different conditions, and you'd harvest this thing, and basically 1 year of growing wheat or something results in 1 data point, okay? And so it was really, really, really difficult, and your entire, like all of this effort would be like result in like 35 data points, okay? And so design of experiments was a very important subject because you wanted to maximize the amount of information you could get out of, say, 35 data points, okay? And so that's why it was critical to kind of have that subject to be able to say, all right, if we're gonna set up an experiment, how do we design this thing so we can maximize the information that we get, okay? And those data sets were small enough where if I said, here's 35 numbers, calculate the mean, you could do it, right? It's a little pain, but you could do it, okay? But now we're at a point where we don't have 35 data points, we have 35 million data points, okay? And it's not possible to calculate the mean by hand of a 35 million data points. You need to use a computer. And all of our data sets, in order to kind of work with them, we need to be able to express what we want to do in the language of computers to be able to handle it. And that's kind of what this hacking skills is all about, okay? We still need to be able to know what we're doing, and that's what all of this math and stats stuff, knowledge is, right? You have all of this theoretic stuff, you learn about your distributions, you learn this and that, and that's important. And when you kind of combine those two, you know, we can get machine learning. We can be able to kind of do that. And when you combine that with somebody who understands, or if you yourself understand the underlying data, if you're an expert in kind of baseball and you're a fan of baseball and you watch all this stuff and you can say, okay, you know what, this person's got a OPS of, you know, 1.2 or whatever, and so that's what this means, and they're really good, or then you can do real kind of data science, right? Without the hacking skills, you know, kind of 101B falls under this traditional research area where, you know, you could do stuff. And then this is he writes the danger zone, right? If you're kind of just applying, like you just read the documentation on, say, scikit-learn for Python, and you say, all right, here's some data and let's just throw it at it, but you don't really understand what you're doing, that could get you into some trouble. Anyway, the stats and data science major and data theory major, you know, really emphasizes kind of these top two, the coding ability, math and stats knowledge, and kind of machine learning. There's just too many different subjects out there. We can't make you an expert in every single subject out there. So it's really up to you to become, you know, subject matter experts on, you know, whatever it is that you're interested in. And so, you know, you think ahead and you say, hey, what kind of, you know, what kind of careers am I interested in? You can kind of start looking for data and start, you know, learning that about that. Okay, so I think I've talked a lot about that kind of stuff. So this class presumes that you are comfortable writing code. You know, Stats 20, Stats 102A, you probably had to write a bunch of functions and things like that, and you're gonna have to be comfortable taking your ideas and expressing them into code. You know, this class is done using R. I know a lot of people want more Python. We haven't gotten the department to make that transition or change yet. But I will plug, I do teach courses in Python. And so, you know, there's Stats 21, and I think they're realigning the numbers so that you could take, I don't know what they're going to call it. Maybe they're going to number at 131 or something, and it'll be an optional upper division elective. Maybe. Okay, don't quote me on this and say, hey, Professor Chen said this. But we're trying for that. Okay. Okay. All right. Here's the idea. Okay. All of the algorithms that we're going to teach you, like k-nearest neighbors and I don't know, the naive Bayes classifier and things like that, they're already available as little functions and packages on your computer, okay? But in your homework, I'm gonna make you write code that will do naive Bayes classification, that you're gonna write code that does k-nearest neighbors classifier, okay? And you're gonna have to kind of do this by hand. And I think there's merit to learning, like, to writing that code yourself, because you're gonna really learn how those algorithms work, okay? By having to kind of create it yourself. It's kind of like, I don't know, you can, I don't know if you ever built like I don't know, you built like a little toy, like a motor. I don't know if you ever built a motor by like winding wires around a thing and you put magnets around it and you made a motor. I don't know. Okay, well anyway, there's merit in like learning some of this, like doing something yourself, building something yourself, and then seeing how it works, okay? Some of the key ideas that we'll cover will be, you know, just key concepts for all of machine learning that applies to anything. It will be like loss functions. Actually, we might skip likelihood functions, but cross-validation and regularization, and then we'll learn specific models, okay? Linear regression you're already familiar with, but we will approach linear regression from a machine learning perspective to kind of get your bearings in there, and then we'll look at other things. And we'll touch on neural networks, which I think is fun, and then we got classification and clustering and EM algorithm, PCA, things like that. There's overlap with 101C, but again, 101C is more on application, and this one is more on, at least the way I approach it, the kind of the inner workings of these algorithms, okay? If you're a stats and data science major, or even data theory, you have to take a lot of these courses, and this is kind of just an outline. So 100 series is all about kind of mathematical theory. Again, 101 series was more of greater focus when data is expensive and interpretability is important, where you kind of like linear models, what's the relationship there, okay? 101C in this class is you have large data sets, data is cheap, but the ability to make good predictions is more important, okay? And then we also have kind of the Bayesian Monte Carlo methods in 102C, which I'll be teaching in the fall, I believe. So I don't know if any of you are going to be taking 102C with me at 8 a.m. in the fall. So, okay, a little bit of academic integrity stuff. This is kind of an appeal to you, right? A lot of the homework problems I give you, they're going to be tough. They're going to be challenging, okay? And that's by design. I want you to be challenged when you do your homework, because I truly believe that is where a lot of the learning happens, okay? And truth is there's a lot of kind of good quality code out there already. And if with a little bit of searching on the internet, you can probably find all of the answers that you're looking for, okay? But that kind of defeats the point, okay? If the goal were to accomplish some kind of task, that's fine, okay? If the goal is, you have a job and you need to analyze this data using this model, yeah, use the package that's already there, okay? Go on Stack Exchange and find your answers, okay? But that's not the goal. When I give you homework, it's not that I need this IRIS data set analyzed, okay? I don't actually care. The goal is your learning, okay? And it's kind of like going to the gym, right? And I give this spiel at the beginning of most of my classes. So if you've already heard this, my apologies, but you're gonna hear it again. If you go to the gym, all right, the goal of lifting weights at the gym isn't so that the weights get lifted up off the ground, okay? That is not the goal. The goal is, the reason why people lift weights is that process of lifting weights leads to the ultimate goal of gaining strength, okay? And if your workout is very easy, okay, and you don't break a sweat at all, you probably didn't exert that much effort, and you can't expect to make much gains or much improvement there, okay? When you work out and you tire yourself out and you experience soreness, that's going to signal to your body that it needs to make repairs, and it's going to come back stronger, okay? And similarly, with your brain, if you don't do anything that challenges it, okay, your brain's not going to feel the need to make new connections or learn something, right? Sometimes as you're like trying to learn something, you're struggling, and then at some point it suddenly like clicks, and like you like get it and you're able to do it. That's your brain making a connection, right? You got these neurons and it's forming new pathways, and it has to do that through the struggle. And making those new connections is work for your brain. And so if it doesn't see the need to it, right, as you're struggling and it's like the paths are all going all over the place, and you're struggling, and it's tiring and it's frustrating, but suddenly like it's like, oh, you know what, let's make this new connection and we get it now. That's how you get better, and you'll become a better coder. You're going to have better understanding for all of this, right? So it's good. The struggle is a good sign, okay? Copying code, plagiarizing code, asking the AI, ChatGPT, hey, help me figure this out. That's like going to the gym and saying, oh man, these weights are heavy. Hey, can you pick them up for me? Can you lift these weights for me? And then you go, yay, the weights got lifted. I had a great workout. Let's go home, okay? And again, if the goal was the weights needed to get lifted, fine. But again, that's not the goal, right? The goal is that process of lifting the weights yourself is going to make you a stronger. And so, similarly, you don't want to have the computer give you the answers or search for the answers or something like that, okay? You want to, you kind of want to struggle and work through it yourself, okay? Sometimes students do resort to plagiarism, and I think that's because they've confused the goal of the course, right? They got mixed up and they believe, it's more important that I get a good grade than it is that I learn, okay? And that's, and I want to just say, hey, the reason why I hope, the reason why you're coming to university, and you're at UCLA, which, I'm a big fan of UCLA, of course, and it's a great school. And the reason why you're here and you're paying money and all of this stuff is so you gain education, okay? And I think that's your learning and your development is more important than just whatever grade you get, okay? So and I admit a major conflicting issue is that I'm not able to create little individualized grading schemas for every individual student and say like, okay, you learned and therefore you get this much, and that would be too kind of messy, and people would be say that's unfair because I came in more knowledge, so I have to do even more than this person who came in less knowledge and only had to do this much or something. But I do hope you'll be able to look at the class and say, hey, I learned stuff, okay? And you can judge your performance based on that, okay? So anyway, please work hard. That's all. Don't cheat, okay? And you know, if we do have to escalate issues, we'll escalate issues, but I really don't want to have to do that, okay? There's a collaboration policy and stuff, and basically says like you're not going to look up past answers, you're not going to look up past exams and things like that, okay? You can share code that's not for the homework, right? So if you're just like, hey, how does this function work? Okay, there's a bit of code in the lecture. How does that work? I don't quite understand what's happening. Go ahead, talk about that, all right? On CampusWire, there's going to be a discussion forum. Ask questions about that. It's just when it comes to the homework problems itself, don't discuss the code, okay? I do also give this little spiel, and so please bear with me here. This one, I just want to say, you know, your grades do not define you, right? You're here at UCLA, and really, in order to get into UCLA, and I think they just released like fall admission numbers, and it was like 8.8% admit rate or something for freshmen, which is, that's like, wow, right? That's, we're truly like climbing into like super elite category, right? And basically everybody who got in, you had good grades, okay? You had good grades either in high school, good grades at your community college or something, and you put a lot of effort into that, and you got here. You deserve your spot here, okay? So grades feel super important to you, but that said, your grades do not define you, and I get it. You know, it feels good to get good. It feels good to get good grades. That's true, right? And grades do play a role, you know, if you're like applying to grad school and stuff, but they're also not the most important thing in life, okay? You're not gonna like, upon retirement or upon, you know, like as you approach death or whatever, you're not gonna look back and go, oh, I can't believe I got a B plus. I should have done whatever to get that A minus, okay? That's not gonna be the thing you regret, right? Hopefully you don't regret too much, okay? But the thing you regret will not be grades in some 102B class, okay? You know, sometimes I tell a story a little bit about my own life. I had to learn this lesson about your grades not defining me. I had to learn it the hard way, in that my freshman year of college, so in high school I worked hard and I got good grades, and I got into my dream school, which was Caltech, okay, over in Pasadena. And I was really excited, and I went there, and I don't know, I struggled my first year. They were on quarter system. Fall quarter, I got my first C ever, and that was humbling. And then winter quarter, I got my first D ever, and I thought, oh my gosh, this is going terribly. And then spring quarter, I don't know, something happened. It all kind of fell apart, and I like failed multiple classes. I got put on academic probation, and I fell into depression. I couldn't see myself separate from my grades, and you know. Prior, you know, in high school, it was kind of like, you know, I'm not a star athlete. I'm not super popular or anything like that. But I have good grades, and I'm okay with that, right? Like that's who I am. I had tied so much of my value, my own personal value and worth, to my grades, and I felt like, okay, well, I'm getting good grades in high school, so that's great, okay? And so, you know, during my freshman year, when I failed a bunch of classes, got put on academic probation, I saw myself as a failure because I had tied my identity to my grades, and that was, and I didn't know what to do. You know, my father was very supportive during that time, and I'm grateful. And I remember I don't remember the exact words, but it was something along the lines of, you know, it's not worth it. You know, all of this dream of going to Caltech, this dream of whatever it is you have, it's not worth kind of this emotional pain and turmoil that it's putting you through, right? And so ultimately I ended up dropping out, and then I transferred to another college. I ended up in Michigan. I went to an engineering school, and I did better there, and things turned around. And that very kind of painful lesson and painful time, looking back, now I'm like 20 years away from that time, but I still remember very clearly. Looking back, I wish I didn't have to go through all of that pain, but I'm grateful that through that lesson, I was able to kind of separate myself. I was able to see myself separate from my grades, and I've kind of carried that lesson, and so how I view myself today is not based on my career success or things like that. I view a lot of my worth, I find intrinsic worth in myself, a lot of it through my faith, also through my relationships with people and my family and things like that. But separate from kind of, academic success or career success or things like that, okay? And some of you're doing fine, okay? And some of you might have an unhealthy relationship with your grades, okay? And I don't know how it is for each of you, but I want to encourage you to be able to view yourself separate from your grades and not have this kind of unhealthy view of self that's super tied to your grades. If you want to chat more about this, I'm happy to. But anyway, that's me on my soapbox and unsolicited advice. You're going to get a little bit more here. There's also this question of work-life balance, and this is going to be something that maybe some of you struggle with right now in college, but it's going to be a thing for the rest of your life. Okay, there's going to be you got to figure out work-life balance, and I personally feel like, I don't want to say I figured it out, but I'm happy with my work-life balance. And the thing is that, throughout your life, there's going to be a whole bunch of stuff that's demanding your time and energy. Okay? And I broadly put it into 3 broad categories: work, relationships, and self. Okay? Work is going to include literal work like jobs and internships, but also, right now school and academics is kind of in this work category. Any other kind of professional obligations fall there. Relationships will be your family, your friends, if you have a romantic partner, that, any other social obligations. And so, like clubs, school clubs could fall in both work and relationships or something. And then you have care of self, right? Your physical health, which will be like food, sleep, exercise, things like that. Your mental health, which will include things like sleeping as well, but also playing, all of your hobbies, your entertainment, all of that. Spiritual health, if that's a thing for you. Okay, and then the thing is there's 24 hours in a day. Okay, and it's not going to be possible to give 100% to all of these different things that demand your time and attention. So you have to make choices. Okay, and this is truly what I believe. Work-life balance isn't like the universe isn't going to just balance things out for you. You have to choose what's important. You have to choose what's important, and you dedicate your time and energies accordingly. And in general, the more time and energy you put into something, the more you're going to get out of it, right? If you have a romantic partner and you spend a lot of time with your romantic partner, your relationship with that person is going to grow, okay? And if you don't put any time, if you have a romantic partner but you don't spend any time with that person, okay, your relationship with that person will not flourish, okay? That's generally just how it goes, okay? Things in general, sometimes there's toxic relationships where you put in a bunch of energy and things don't work out. But in general, more you put in, the more you get out, right? Schoolwork, the more you kind of study and stuff. In general, you'll do a little bit better. If you don't put any effort into your class, you're probably not going to do great in that thing. That's just in general. And I think satisfaction with your work-life balance can be achieved when you accept just the natural consequences of what happens when you put less time and energy into something. Okay, when you put less time and energy into something, you're going to say, okay, well, this thing in my life is probably not going to flourish, and I'm okay with that. Okay, because it's, to me, at this point in my life, it's not as important as these other things, and I'd rather put all of my time and energy into these other things. And so if these other things that I'm not putting time and energy into don't flourish, I'm okay with that. Then you can achieve that work-life balance, right? So, okay, just silly example again. Maybe you have a group of friends, and you put in a lot of time and energy into your friends, and you're like, really close to each other, and then you get involved in a romantic relationship, and so now you're spending a lot of time with your romantic partner, and you don't have as much time for your original group of friends. And so what naturally happens is you're not as close as you used to be over here, and you're more close over here. And that could reach a point where perhaps your friends go off and do some activity without you. And that could feel hurtful at first. But it's probably not that they're like trying to be like malicious or something, okay? But that's just naturally what happens. If you're not as close as you used to be, you're not going to be invited out as much, okay? And the great thing is you have freedom. You get to choose what's important to you, right? You get to choose. And I think people who struggle with work-life balance feel like they don't have a choice between what's important. Regarding what they want to spend, how they want to spend their time. If they feel like I can't say no to work, so I have to spend all of my time at work, and everything else gets neglected, then it's hard for them. But the thing is you can always say no to work. Okay, you can always say no. There's going to be consequences to it, right? And maybe you don't get that promotion. Maybe you get fired if you say no too much to work, right? But you can always say no, right? You can always say no. And that's just, again, there's consequences to saying no to certain things and not giving all of that time. And you just have to be okay with that. And you can say, well, this current job is too demanding. I want to say no. And maybe that means I'm going to just stay here and I'm not going to move up. Or maybe saying no means I got to find a new job or something. But that's what happens, right? So here it is, at work. At work you might have to compete with somebody who has no life outside of work, okay? And so all of their waking hours are spent at the office and things like that. From the company's perspective, they probably love that, okay? But from a human perspective, I don't know if that's great, okay? It's good to have things outside of work. And so maybe that means, okay, this person who spends their entire life in the office, I'm okay with that. And I'm okay not being that person. And that person's going to probably get promoted before you. Probably, okay? I don't know, okay? Or you can say, hey, you know what? For me, right now in this stage of life, I don't have any other outside commitments. I'm ready to devote all of my energies to work, and work is exciting to me. I love it. I love this company, and I'm willing to spend tons of hours, and I want to see this, this company flourish and things like that, and I'm willing to give a lot to it. And probably hopefully your company grows and you do well and reflect it, and then once you achieve a certain level of success there, you can say, okay, well now I can start doing all these other things that I neglected earlier, right? These are just paths that you can choose, right? And then over here I wrote self-care is important, okay? So, we have these things, work and relationships. Those aren't the only things. You got to take care of yourself, right? And important is sleep. Make sure you get lots of sleep. This is something that I think a lot of college students neglect. You have to think of sleep as like an activity. Like you're doing your homework, like sleeping is like your homework too, okay? And you want to make sure you're getting enough sleep to do well, because sleep is when your body makes repairs physically, and it's also when sleep is when your brain does a lot of kind of the neural connections, right? So as you're learning stuff, if you're not getting sleep, you're not giving it not giving your brain a chance to kind of like do that, I don't know, biological process of making those connections where that learning really kind of settles in and you memorize stuff, right? And if you don't get enough sleep, you're gonna get probably sick more often. You might be grouchy. You'll be a drag to hang out with. So make sure you sleep. Okay. And sometimes taking care of yourself means not doing your homework. Okay. And that's okay. All right. Now the consequence of not doing your homework is your grade will go down. Okay, that's just what happens. Okay, that's just what happens. But I want you to be in this position where you can say, to me, getting the sleep or hanging out with my friend or being, supporting someone or whatever is more important than, the grade on this homework assignment. Okay, and you make that choice, right? Or you can say, hey, homework, I really need to get the good grade and I really need to do the homework. But that's a decision. Okay, so when I say something like, take care of your physical and mental health, what I personally am saying is that I think your physical and mental health is more important than your homework grade, okay? That doesn't mean you don't have to do your homework and I'm still gonna give you 100%, okay? If you don't do your homework, your grade's gonna go down, okay? But I want you to be okay with that kind of decision, okay? That's just how those natural consequences work, okay? And then this last slide on all of this, again, life philosophy stuff. Just be aware of, there's kind of this category of time suck, that I call fruitless entertainment, okay? Having fun and play is, I think, super important for our mental well-being, right? We need to kind of have a break from work and give our brain some time to just have fun, okay? And so things like, hanging out with friends or watching TV, watching a movie, playing sports, playing video games, whatever it is that you like, going on a hike, all of those things, reading a book, those are good things, right? And when you do an entertainment activity, it should be a break from work and you should come back feeling better, okay? You should come back feeling in a good mood, okay? And but there are some activities, and I put this, I hope, even hanging out with certain people can have an opposite effect, right? And these activities end up actually draining you, right? There's kind of like a whole class of apps, especially like certain social media apps, that are designed not to make you feel better, but designed to just keep you hooked on the app, because that's how they make the money, right? The more time you spend on the app, they can feed you whatever advertisements, this and that, and I guess thanks to data science, they've made these they've gotten really effective at keeping you hooked, right? They have like infinite scroll. Basically, it used to be you scroll to the bottom of the page and you have to click next. And they found out, having to click next is where we often lose our users, right? Rather than clicking next, they reach the bottom of the page and then they turn it off. And so they do infinite scroll. So there's no bottom, okay? And there's no pause. And so anyway, these things, or whatever video game where it's like you play around and then your team wins or loses, and then you play another round and your team wins or loses, and it just kind of keeps you kind of in this thing. And all of these things are designed to be around, I don't know, 20 to 30 minutes or something, which is kind of like this natural kind of time span that kind of is like, I just need a little bit more, but not so much. Just like the TV episodes on Netflix and stuff, they're all kind of 20, 30 minute things. And so they, it hits your brain with these dopamine hits, so you keep coming back. But at the end, you're like, oh my gosh, how did I spend 4 hours doing this thing? Or, I started off at 10 and now how is it like 2 a.m. now? And you don't feel great about yourself, right? So be aware of stuff like that. And then when you realize like, okay, you know what, it's kind of fun in the moment, but afterwards I don't actually feel great. I don't feel like it's doing me good. Be aware of that, and not saying you have to delete all of your accounts, but just be mindful, right? Just be mindful of these things, okay? I ended up deleting a bunch of my accounts because I was like, oh yeah, you know what? This is not a good thing, but if you can do things in moderation, that's great. Okay. Okay, let's now get into the content of our class. Let me give you your second view quiz answer. Second answer today is the letter D. D as in dog. D as in dog. D. Okay, so this was a definition that was on Wikipedia for machine learning. Maybe it's different now, I don't know. Machine learning, it says, is the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without explicit instructions, relying on patterns and inference instead. My translation or whatever is that we're basically trying to fit models to the data, okay? And now people still have to make decisions regarding what model to use, okay? But once you kind of decide what model to use, a lot of the decisions are guided by the data and the algorithms used, okay? Algorithms are basically just instructions, okay? Just instructions, okay? And when you follow these instructions, when you follow the algorithm and decisions are being made by following these instructions, that is the machine learning. That is the machine learning, okay? So what is a model? This is a picture of a model airplane. And a model airplane and a model in general it's a simplified representation of something complex, okay? So a statistical model is a simplified representation of some kind of likely complex real-world process that generates data. So there is often, in real life, we might say, let's have a data set, okay? Like, let's measure how tall someone is, okay? How tall is someone? And there are all kinds of things that play a role in determining how tall someone is, right? And it's a complicated process. It's like your genetics, right? Your nutrition, I don't know, this and that, right? All of these different things. And genetics is just this broad thing, but it's like, okay, maybe we can look at your biological father's height and biological mother's height. We can look at, certain genome sequences that are responsible for height. I don't know, right? It's this complicated thing. And maybe we just say, oh, you know what? Let's simplify this. And we'll say someone's height is going to be just overall, we'll look at, we'll look at their, let's predict someone's height by looking at their arm length or something like that, right? And it's not that arm length is responsible for height. Obviously something is, there's all kinds of different factors in there, okay? But the ultimate kind of process is complicated, and we're just looking for some way to kind of simplify this, right? So a statistical model is a simplified version of relationships between variables in the real world. It includes only a subset of variables that are related to the outcome, and they're always going to include some kind of error term to account for everything else, okay? And in real world stuff, we often think of like this causes this, and this causes this, and this causes this, and this is the output, okay? In statistics, we don't actually care about what causes what and what, we just say, hey, here's our output. Here are other things that we can measure and record, and are any of these things kind of related to this output, right? And it could be like this output actually causes these other things, but we're able to measure these things, and we're not really able to measure this thing easily or something, or we want to be able to predict this thing. And we can say, okay, well, based on these other variables that we're seeing, what can we do, right? So this is a statistical model. We're just trying to figure out relationships so we can make kind of good predictions, okay? or we can understand some kind of relationship. So the quote, all models are wrong, but some are useful. And I'd say kind of the two primary uses for statistical models. And statistical models, we can also call them machine learning models. We can use them for making predictions, and then we can also use them to help us gain understanding for what relationships exist between variables. And oftentimes we have certain models that are better at predictions and other models that are better at understanding the relationship. And so your choice of model, which of these priorities are more important, will factor into which model you end up choosing. Okay, so let's look at a simple example from our textbook. Oh, I'm sorry. So we have a textbook, and it is called A First Course in Machine Learning. And I usually try to get textbooks that are free, but I couldn't find one that was free. So here is I don't know, this is what it looks like. A First Course in Machine Learning. That's like the digital version. And do you have it? How much is a paperback? Okay, paperback, $36 is reasonable. Okay, but this is the textbook, and so I'm taking this example from our textbook. Okay, and we're gonna look at Olympic races, and we're looking at the men's basically 100-meter foot race, and we're looking at the gold medal time at the Olympics men's 100-meter track and field event. Okay. And there's lots of different kind of factors that go into what determines the winning time, right? But we're going to just make a simple model, and we're plotting the winning time versus the year the event took place. And what do we see? We see in the 1896 Olympics, the winning time was 12 seconds. And then in 1900, the winning time was 11 seconds. And they just didn't have accurate stopwatches back then, okay? And then now we can measure things to like the thousandth of a second and stuff. But we see over time, like the winning gold medal race times got faster, okay? In general, okay? Now here it got like a little bit slower, but overall, as time went on, the winning race times got faster, okay? Now, so we can say, well, if we know the year of the Olympics, we can kind of predict the winning race time, right? And we might say, well, let's fit a linear model. A linear model is a straight line model, and that just kind of means like how much do we adjust our prediction? That's going to remain constant through time. So if we're going to say from 1920 to 1924, if we're going to say the winning time improved by 0.05 of a second, 0.05 seconds, okay? Then when we go from 2000 to 2004, it's also going to improve by, 0.05. All right, so we're just saying it's constant over time. Okay. Now this is not going to work for predicting things, far into the future, because far into the future, if this is still the case, we would end up with negative race times, and that's not possible. But for this span of 100 years or so, it seems reasonable. Okay, and so we're going to say, all right, let's fit a model to the data, right? Let's fit this straight line. And so fitting a model is estimating what parameters, estimating the values of the parameters. In our case, we're fitting a straight line, so the parameters are the slope and the intercept. And so now we need to figure out what slope and what intercept do we want, okay? So we want the line, the slope and intercept, so that the resulting model, the resulting line, does the best job of fitting the data. So what does it mean to say this line does the best job, right? So we want the best parameter estimates, and how we define what best means Okay, that's very important, and that's going to determine what we call the objective function. Okay, objective function is basically the function that defines like the goal that we're trying to either try to maximize or minimize. So for ordinary least squares regression, which is kind of your classical regression model, we define the best model as the model that minimizes the total squares of residuals, right? So the residual is the actual value minus the predicted value. Okay, so if we're say in 1920, we predicted, I don't know, in 1920 we predicted, I don't know, 10.5 seconds, and the true time was 10.7 seconds. Okay, we have a residual of 0.2. Okay, and the total sum of squares is basically, okay, each value, the actual value is yn, our predicted value for the nth observation is y hat n. We take that difference, we square it, and then we're going to sum it up. So this is the residual sum of squares, right? Sum of squared residuals is your RSS. Okay, so this is our objective function. This is the thing, and we're going to try to minimize this objective function. So sometimes this is called a loss function or a cost function. So you might, in other textbooks or things, they'll say, okay, we define the loss as this, or we define our cost function as this, because generally we want to minimize our losses, we want to minimize our costs. So that's what we have. Okay, so linear regression technically counts as a machine learning model, and a bunch of other machine learning models that we have basically try to fit parameters by trying to minimize, or in some cases maximize, some kind of objective function, right? And so a lot of our machine learning problems can be reframed as optimization problems. So this class is, I think, called Computation and Optimization for Statistics, and basically a lot of our machine learning stuff is some form of optimization, okay? And so even though linear regression is review for you, we're going to start here so you can kind of get familiar with the ideas and concepts in machine learning, okay? So here I'm going to try to match our textbook's notation. So, you know, for linear regression, you're probably accustomed to y minus y hat. And here, you know, our textbook uses t and f and things like that, okay? So the actual data, so the actual values are called t, like t sub n. So t1, t2, t3. T kind of for target. This is the target value that we want to achieve, okay? And then we get values predicted by our model. So our model is our predicted values rather than y hat. We're going to say the values created by our model is the result of plugging x into some function, okay? And so here we're going to say the values predicted by are going to be f, the function applied to xn, and then the semicolon here says we have these parameters w0 and w1. So here these w0 are basically our weights for what our intercept and what our slope are, right? So in linear regression you probably had beta 0, beta 1, and things like that. And it's the same thing, but here they're just w's for the weights, okay? Because when we generalize to any kind of model, it's just some arbitrary number, some constant, that we're going to just call a weight. And then the textbook likes to use mean squared error rather than the total squared error, which is fine. It's just same thing as residual sum of squares, you just divide by n. So our loss function, our L for the loss function is going to be 1 over n to get the mean squared error, okay? And in textbook notation, it's 1 over n, the sum of our target value minus our predicted value, which is f applied to observation xn, and then with our current parameters w0 and w1 for a linear regression model. In a more complicated model, there might be more parameters in there, and we're taking that difference and we're squaring it. Okay. Another common metric that we see is root mean squared error, RMSE, and so this is I don't know if you've ever gone on to Kaggle and done a competition or something. This is generally the metric that gets used for evaluating your performance is root mean squared error, RMSE, and that's just the square root of mean squared error. Okay, just take mean squared error and you just throw it into the square root function. So target minus the predicted things in there. Okay, and basically the values that minimize mean squared error will be the same values that minimize RMSE. Okay, and you know that's because the square root function is monotonic. So if there's any two values, if b is less than a or a is greater than b, then the square root of a is also going to be the square root of b, okay, for any value where a and b are positive. So the values that minimize MSE, mean squared error, will be the same values that minimize RMSE. Okay, linear models have in these two parameters, an intercept and a slope. Intercept is our W0 term, slope is W1. And so this function, when we write function of xn of w0, w1, is just basically this, w0 plus w1 xn, okay? And so if I plug that in, we can say our loss function mean squared error is the difference between our target minus, this is what we predict, w0 plus w1 xn. We're going to take that difference and we're going to square it. And so how do we minimize this, okay? Well, I don't know, did you guys do this in 101A? Or is this like 100C? Or I don't know where you do this. Okay, basically you do some calculus, right? You say, all right, let's figure out the formula for our slope and our intercept to minimize this thing. Okay, we could, right? So we want to find, so argmin is basically saying find the values for these two arguments, W0 and W1, that will minimize this quantity over here, okay? And so we'll say, okay, well, let's expand out this loss function. So if I do t minus w0 plus w1xn times t, and I expand this out, this is what we get, okay? And then what would we do if we did calculus? We would take the partial derivative of this loss function with respect to w0. We would also take the partial derivative of this thing with respect to w1. Okay, we would set those derivatives equal to 0. Okay, and now we have two equations, you know, simultaneous equations. We would solve them, right? We would solve these simultaneously, and I've kind of skipped all of that work. If you want to refer to the work in your textbook, you can. And this is not the point of the lecture, so I'm kind of skipping all over those things. But if you do it and you solve, okay. Or if you do the partial derivatives with respect to w1, you get this. Partial derivative with respect to w0, you get this. And you set these things equal to 0. You solve for w0 and w1 to get your estimates for what your estimated slope would be and what your estimated intercept would be. Okay, and they kind of follow these kind of your classical formulas. Okay, so I skipped a bunch of these things. You can look in your textbook for the details, probably past notes from another class. I want to look at this again, but we're going to do using linear algebra. Okay, and so because we're dealing with a whole bunch of observations, right, when we look at the loss function, we have these summation things, because we're saying take the difference for our first observation and then add it to the square difference for a second observation, and then add that to the third observation. So you have these big summation signs, which they can be annoying to deal with, right? It can be annoying. And so it's going to be helpful for us to use matrices. Okay, and because when you do matrix multiplication, the summation happens in that multiplication step, right? If you take a vector, row vector and a column vector, and you multiply them together, you're multiplying all of those elements and you're summing them up in that matrix operation. Okay, some of you took linear algebra just like last quarter. And others of you, it might have been a while since you've done linear algebra, okay? So highly recommend reviewing all of your linear algebra stuff. There is a playlist on YouTube from 3 Blue 1 Brown. This is like one of the best series of videos on linear algebra, and I highly recommend it. If you haven't, well, you should subscribe to his channel, and then you should watch these things to just kind of review these things. The videos are about 10 minutes each. Some are a little bit longer, some are a little bit shorter, but they're all really great. Highly recommended. Okay. So we're going to do ordinary least squares regression in matrix notation. I recognize some of you have taken 100C and you've already seen all of this stuff. Others of you have not taken 100C, so I'm going to present it to you here. But we're going to look at this, and it will be important for our class. So we're going to put our two parameters, the intercept and the slope, together into a vector. Okay, this little column vector W. Okay, so W is W0 and W1. Okay, and then we have one observation is this little column. Okay, so this is basically the value 1 and the x value itself. So if we're talking about the Olympics and the foot race, you know, your xn will be something like the year 1900 or the year 1944 or the year 1988 or something like that. Okay, and so that will be that. And then therefore, when we talk about what function, or what is the function that gives us our predicted values, which is W0 plus W1xn, we can say, oh, you know what? That is W, our vector W multiplied by vector xn. So W transpose xn is going to be our predicted value. Okay, so we're going to transpose it, and then we get a 1 by 2 multiplied by a 2 by 1, and we get a 1 by 1 scalar value. That's our predicted value here. Okay, so if I have a whole bunch of these observations, I'm going to gather them all into, whoops, I don't want to do that. Okay, I want to move that down there. We're going to put all n observations together in one matrix X, okay? And so now, each of these things will be a row, okay? So x1 transpose x2 transpose, so on and so forth. So I'm going to have a column of 1s and then a column of all of my x values, okay? And then meanwhile, I have all of my target values, okay? This is all of basically our y values, the actual outcome values. And so our loss function will simplify to this, 1 over n t minus xw transpose t minus xw. So let me just let me show you this on the next slide. Okay, so here xw, when I take matrix X and I multiply it by our column vector W, okay, I get 1x1 times this, and I get W0 plus W1x1, and then I get W0 plus W1x2. And all of these are just scalar values, and so I get just one column of values, right? N of these things. Sometimes, because elsewhere in regular algebra, x times w is the same thing as w times x, but it's not the case in linear algebra. You can't just switch the order of these matrices, right? That should have been hammered into you in your linear algebra class. So I think it's very helpful to write the dimensions of your matrices underneath them, so you can make sure that your multiplication aligns. So x is n by 2, n rows, 2 columns. W is 2 rows, 1 column. And so when I multiply x and w, I get n rows and 1 column of values, right? So these inner dimensions, the number of columns over here must match the number of rows over here for it to multiply. So here xw becomes n by 1, and that's what we have. If you do this in R, here let's just look at what I did. Olympic $year is going to be a column of all of the years, 1896, 1900, 1904, 1908, so on and so forth, okay? And then I create a column of ones. I have n values of the number 1, and I bind columns, okay? C bind the ones and the X column, all right? And that's going to be big X. The dimensions of big X, 28 rows, 2 columns, okay? W, I just put in the number 1, 2 rows, 1 column, okay? And so here in R, I do X. This is your matrix multiply operator, percent star percent, X times W. 28 by 2 times a 2 by 1 results in 28 by 1, okay? However, if you mix up W times X, W matrix multiply X, you get this error. Error in W times X non-conformable arguments, okay? This error, and I don't know how you feel about R error messages, okay? But R error messages, I think, are actually very helpful. They tell you exactly what went wrong, okay? So when you encounter an error message from R, don't just throw up your hands and say, I don't know what's going on. I don't know what's wrong, okay? Read the error message and see if that can help you, all right? And if you see a thing that says non-conformable arguments, that means the dimensions for your matrix aren't aligned. You're trying to do a 2 by 1 matrix multiplied by an n by 2 matrix, and that's just not going to work, okay? So you'd say, okay, well, what are the dimensions of W? Oh, 2 by 1. What's the dimensions of X? N by 2. And you go, okay, yeah, that makes sense why I can't multiply those operations. So if you encounter this error message, that means your dimensions in your matrix multiplication didn't work. Okay, so anyway, going back, this value, t minus xw, is our column of t's, and then xw, we said, is basically our column of predicted values, and so t minus xw just becomes the column of residuals, okay? The actual values minus our predicted values. Okay, and so, t is n by 1, xw is n by 1, so you can just do the matrix addition or subtraction there. We get n by 1 column there. And then, and so what is this? This is the sum of squared errors, right? So the sum of squared errors, if I expand this out, okay, we have t1 minus our predicted value for observation 1, t2 minus our predicted value for observation 2, all the way up to tn minus our predicted value for observation n. And then here I have a column here, right? This thing is just the transpose of t minus xw transpose, and this is just the column of t minus xw transpose. And so by having t minus xw transpose times t minus xw, and I do the matrix multiplication, it's going to multiply the first element times the first element, which is this thing squared, plus the second element times the second element, so which is this thing squared, plus everything up through this last one squared, okay? So this entire summation here is handled by doing t minus xw transpose t minus xw. And so the summation is implicit, or is just part of the matrix multiplication operation, which is great, okay? So because that's going to simplify our lives. So we can write our loss function compactly with matrix notation, and this will be kind of a scalar value. So here I've got a 1 by n multiplied by an n by 1, so that's going to produce a 1 by 1 value. I'm going to multiply it by the scalar 1 over n, and so my loss function is just a 1 by 1 scalar value, which is exactly what we want. Okay? So I can expand this, t minus xw transpose times t minus xw. I can expand this further, and it becomes this, right? So the rule with transposes, all right, is that for addition and subtraction, the transpose just can get distributed. So we get t transpose minus xw transpose, okay? And then the rule for transposes when you have multiplication is that you apply the transpose to each of those elements, but you have to reverse the order of the multiplication. So this becomes t transpose minus w transpose x transpose, okay? And then now you do your distribution property of things, and say, first the first elements, the outer elements, the inner elements, the last elements. So I've got T transpose T, and so now you can see I'm writing all of the dimensions underneath each of these things, so we just kind of keep track of everything. So T transpose is 1 by n, T is n by 1, so that's going to simplify to 1 by 1, T transpose T. Okay. Here I got T transpose XW. Okay, I've got first times the outer, right? The outer elements. So that multiplies out 1 by n times a n by 2 times a 2 by 1, T transpose times n times x times w. And then I've got over here, I've got W transpose X transpose T, our inner elements, W transpose X transpose T, again, 1 by 2 times a 2 by n times an n by 1. And then finally, our last elements, W transpose X W, and all of these things. All of the order of multiplication here also aligns, and these all become 1 by 1 scalar values. And these two things, T transpose XW and W transpose X transpose T, I can combine. All right, I have it written on the next slide. But basically, this is a 1 by 1 scalar value. This thing over here, W transpose X transpose T, is also a 1 by 1 scalar value. And these are transposes of each other. Okay, right? If I transpose this, I would get, you reverse the multiplication. And they're just transposes. And basically, it's a scalar value like the number 7. And what's the transpose of the number 7? It's just the number 7. So it's these two values are exactly identical because they're scalar values and they're transposes of each other. So I'm going to just combine them. I arbitrarily choose 2 W transpose X transpose T, but I could have just as easily picked this one, 2 T transpose X W. Okay? And so here I have this. This is our loss function in matrix form. Okay, 1 over n T transpose T minus 2 W transpose X transpose T plus W transpose X transpose XW. Okay, so that's our loss function expanded out. So, so now what we want to do is we want to find the value of W, okay, that will minimize the loss function. Okay, so how do we find the value of W that's going to minimize this? So we're going to do some vector calculus. Okay, we're going to take the derivative of the loss function with respect to now the vector W, and then we're going to set that derivative equal to 0, and then we're going to solve for W. And so we'll minimize the loss function doing vector calculus. Okay, so how do derivatives work? So if you think of just a regular function where you have a scalar input and a scalar output, right? So you're going from x to y, okay? The real number input, real number output. Then the derivative is basically, okay, you add a tiny little h to x. How much did your function change, right? So you have f of x, and you add a tiny little h to x, and you say, how much did my function change? Divide by how big was that little h that I added, right? And you take this limit as h goes to 0, right? And so similarly, that's going to be your f prime, and you can kind of do some algebra and rearrange it, and you can say, well, we want it so that this quantity, when I do f prime of x times h, this whole thing, we end up getting 0. Okay? Similarly, when we are dealing with vectors, okay, we have the input is a vector, n-dimensional, n values. Okay, so we have n-dimensional real space. We're going from multiple values going into the function, and the output is just a single scalar output. So that's what we have with our loss function. Our loss function is that our input is W. We want to figure out the intercept and the slope. We have two values going in. Depending on what intercept and what slope we have, we're going to have different sum of squared errors, or mean squared error, I should say. Okay, and so we're going to find the h that that satisfies this thing. We don't call it f prime. We call it nabla f. This upside down triangle. It's not delta. It's called nabla. It's the upside down triangle that kind of stands for our multi-dimensional derivative, or I guess what we would call the gradient, okay? The gradient in this space. Okay, now what the gradient ends up being is that if you have some vector, length n vector, then the gradient is just the vector of partial derivatives. So it's just the partial derivative of the function with respect to your first element, partial derivative with respect to the second element, and so on and so forth. So that ends up being what the gradient is. It's just all of your partial derivatives arranged in a vector here. So basically, that's what we're going to go for. We're going to basically, so if I go back a bunch of slides, we're going to be searching for basically the partial derivative of the loss function with respect to W0 and the partial derivative of the loss function with respect to W1. But we're going to try to do it in matrix notation, which we can do. Okay, so like the derivative, so the derivative is like the slope of the tangent line. Okay, the gradient represents the slope of the tangent. I guess the tangent vector. Okay, the vector that points in the direction of greatest increase of the function, right? So you imagine this function, this surface, okay, and you have at a point, what is the gradient? It's the vector of steepest increase, okay, and the magnitude is kind of the slope there. Now, so if you reach basically the bottom of a valley or bottom of like a bowl or the top of a hill, then you no longer have a single you don't have a single direction for a greatest increase or something, right? Because it's that basically your gradient is 0 at that point. All right, so here are this will be helpful when we try to do calculate gradients, or doing some vector calculus, right? If our input is a vector, okay, then what is our output? So just keep in mind the output of the function needs to be a scalar. The input is a vector, and when you do the gradient with respect to that vector, the dimensions of that gradient has to be the same dimensions of that vector. So because the vector, if it's an n dimension, if it's length n, then the gradient needs to be length n. Okay. So here, if the function is w transpose x, and we're taking the gradient with respect to w, then the gradient is x. Okay. And if the function is x transpose w, then the gradient is x also, which is 2 by 1. And if it's w transpose w, then our gradient is 2w. And if we have w transpose matrix C being a 2 by 2 w, so if w is 1 by 2, c is 2 by 2, and w is 2 by 1, then the result is it needs to be 2 by 1, and it's going to be 2cw, c being 2 by 2 and w being 2 by 1. So let me just kind of illustrate this. So for w transpose x, so if w is w1, w2, and x is x1, x2, w transpose x is w1, x1, w2, x2, right? We multiply these elements and those elements, and we add them together. And then we say, okay, well, what is the gradient with respect to w? Well, that's going to be the partial derivative with respect to w1 and the partial derivative with respect to w2. So if I do w1 x1 plus w2 x2, what's the partial derivative of this with respect to w1? It's just going to be x1. Okay, and what's the partial derivative of this thing with respect to x2? I mean, with respect to w2. Okay, with respect to w2, this is a constant. This thing is just going to be x2. Okay, and so the gradient with respect to w is just becomes the first element is x1, the second element is x2, and that's just the vector x. Okay. Technically, it's a column, but I have this just transposed here. That's why I have this thing transposed. Okay. Similarly, and you can do this for any of the other ones, but if I have w transpose w, okay, w transpose w is w1 w1 or w1 squared and w2 squared. Okay. And then if I say, okay, what is the partial derivative of this with respect to W1? Okay, with respect to W1, this is 2W1, and this thing is 0, right? So you get 2W1, the first element. Second element, what's the partial derivative of the second element with, what's the second element is the partial derivative with respect to W2, and so the second element is 2W2, right? And so what is that? 2W1 and 2W2 is equal to 2 times W, right? So these are just derivations of some of these things. If you wanted to try out any of the other ones, you'll find that they also work out, okay? So, so going back here, what we want to do is, okay, well, how many view quiz answers have I given you? 2. Okay. Let me go ahead and give you your last 2 view quiz answers, and we'll end up finishing a little early. We got through my slides a little bit faster than I thought. The last 2 answers, third answer is A as in apple, and the fourth answer is C as in cat. Okay, A as in apple, C as in cat. Okay. Okay, so what we're going to do is, here's our loss function that we expanded out, right? I think I distributed, so we went through this and I distributed the 1 over n, okay? And so now we're going to take the derivative or gradient of this with respect to w. We're going to set that gradient equal to 0, and we're going to solve for w, okay? So the gradient of f, w is a 2 by 1 vector, gradient of f is also 2 by 1. So we're going to say, okay, what is the gradient of this with respect to w? Well, there's no w terms in here, so this just becomes a 2 by 1 vector of zeros. Okay, here I've got 2 over n, w transpose x transpose t. This part is basically just, this part is basically just a n by 2 by 1, what do you call it? X transpose t reduces down to a 2 by 1 vector here. So basically, w transpose gradient of this with respect to w just becomes x transpose t, also 2 by 1. And then here I've got w transpose x w. This is x transpose x is basically your matrix C. This thing, it's basically this. It's just C is x transpose x, and so we get 2 CW, okay, 2 x transpose xw. All right, so here I got, this is 2 by 1, this is 2 by 1, and so this is my result, negative 2 over n times x transpose t plus 2 over n x transpose xw. And now we want to solve for w. Solving for w, we're going to set this thing equal to 0, all right, and I can multiply both sides by I can multiply by n over 2 to get rid of our constant. And then I'm going to add x transpose t to both sides. So now I get x transpose t is equal to x transpose xw. I want to solve for w. So there's no division. There's no division in matrix. There's no matrix division, right? So so that's a mistake that I see students make on exams and stuff, is trying to do division. You can multiply by an inverse. Okay, you can't divide. So we're going to multiply both sides by x transpose x inverse, okay, to get rid of the x transpose x over here, to get w by itself. So on the left-hand side, I'm going to do x transpose x inverse times x transpose t. Here I get x transpose x inverse times x transpose x, so this becomes the identity over on the right, okay? So here on the right, I get w, and then here I have x transpose x inverse, which is going to be a 2 by 2 matrix, times x transpose t, 2 by n, times n by 1. That reduces down to a 2 by 1. Okay, and that's our solution. And so if you've taken 100C, this is all very familiar. You end up with this thing, x transpose x inverse x transpose t is going to be how we solve our estimates for w that will minimize the loss function. So if we want to minimize the mean squared error or sum of squared residuals, then this solution using x transpose x inverse x transpose t will minimize total squared error here, okay? And that's W. That's solving this using just kind of matrix notation. And, you know, we'll build off of this in Wednesday's lecture. All right, I guess we finished a little bit early today. Hope that's all right. I've already posted your first homework assignment, okay? So just, the class goes fast. The class goes fast. So go ahead and take a look. Make sure you answer your lecture review quiz before Wednesday's lecture, and we will see you at noon on Wednesday. Have a great day.